This is going to be a continuation then from what we were discussing before about hypothesis testing. We talked a little bit about the math. We will be doing more of that today. And we'll also be showing you how to do this in Excel and hopefully build a little bit more intuition with it involving some examples. So, what did we discuss last time?
T-value.
The what?
The t-value.
The t-value? We did that last time? I don't think we did. Yeah, that was a couple of times ago. Well, that'll come up again today, though. So not a bad idea to forget about.
Type 1 error.
Type 1 error. We did type 1 and type 2, right?
Yeah. I'm trying to figure this in the trial.
Type 1, type 2 error. Sometimes it's done with Roman numerals. You can do Roman numerals if you want.
We did the 2 telltale and the 1 telltale.
Excellent. And we did the null and alternative hypotheses. So recall one of the big things we did last time is we set up some definitions. What exactly are we looking at? What are we searching for? And what kind of mistakes can we make? So let's start at the bottom and work our way up. What's the difference between a null and alternative hypothesis? Yeah, Sandra?
I just want to know and it doesn't affect, it can't affect anything, nothing else.
So it's best to think about a null as the default position. And that's a little bit of a misnomer. Like, don't get too hung up on what you consider to be the default position. The null is more accurately thought of as nothing interesting is going on.
Oh yeah, and then the alternative is the assertion that deviates from the default.
Yeah, it's just the opposite exactly. It's
And it's HA.
Genuine deviation. Genuine, or should I say non-random. It's essentially saying something interesting is going on. Things affect one another. So if you make more money, you spend more. That makes logical sense. But the null hypothesis of that would be if you make more money, your spending does not change. And you would have to generate evidence that it does matter. And I know that seems strange. Obviously, if you make more money, you spend more, right? That seems so intuitive and logical. But keep in mind that this is kind of a math course. It's statistics is math. And so we want to try to keep our terminology neutral. We don't want to baggage it with any sort of preconceived assertions of how the world works. So when we think a null hypothesis, we want to be able to say null hypothesis is logically defined as having a certain qualities. And that shouldn't depend on anyone's personal experience or cultural understandings or anything really about how the world works. We have to set an equal standard. So if you change your hair to a different hair color, that shouldn't affect spending, right? That only makes sense by default that we wouldn't assume that. And it would be kind of interesting if that wasn't the case, if we found that indeed it did change things. If you put on different kinds of shoes, or if you're taller, or if you saw a baseball game that day, it makes logical sense, right? We would assume, those things shouldn't matter, right? That's our default position. So therefore, we should apply that to things which, while we are tempted to think it matters, we should apply that to things where obviously it could matter, it should matter, but we have to apply it in the same way as well. So we have to say, also if your income changes, your spending doesn't change, would be the null hypothesis there. So again, don't get hung up by thinking about default position as what you're thinking about. Think about default position as nothing matters. Nothing matters. There would be no change. If you do something, nothing will change. If you give people more money, nothing will change. Just like if you change their shoes or change their hair color or show them a baseball game or make them taller, nothing changes. The alternative hypothesis is there is some deviation, there is some change. The world is different. You're working with a new population distribution. You have changed results. Now, what kind of change are we looking at? That's our 1 and 2 tail. So what's the difference between 1 and 2 tail? What counts as a default? What does not?
Well, the 2 tail is unusual.
Mm-hmm.
And then the 1 tail is like test improvement.
Mm-hmm. So could you give me an example?
Let's go with
Give me an example. Anyone give me an example of a 1 or a 2 tail test? Yes.
I can't quite hear you, so.
I think as an example, the baby breastfeeding about the flower, filling in the bag, and we wanted to see if the machine was growing enough flour.
So the flower was growing in the bag.
Well, like, we wanted to see if it was maybe 5 pounds in the bag.
Oh. Yeah. So we could do that where there's a machine. For some reason, you were saying flower. I forgot what my example was, and I was thinking like flowers that like in a garden. And I was like, I don't remember that example at all. Was I there for that? And of course, you're right. It's the machine that's putting, the baking flour in the bag. Doesn't it have like? Oh well, I can't. I think there's a symbol for flour. I can't remember what it is now. So what is that? Was that a 1 tail or 2 tail test?
2 tail.
I was asking Anisha.
Oh.
2 tail. Why was it a 2 tail test? How did you know? Exactly. In other words, both sides of the distribution would have been interesting. We could say, would have resulted some genuine deviation. We can claim there's a genuine deviation in both directions. Too much is just as bad as too little. In both cases, we need to service the machine. All right. We also discussed type 1 and type 2 error. So, what's the difference between the two?
Ooh, this seems like a great time to call on someone. I feel like I haven't been calling on people in a while. Is Joyce here? Okay. Is Austin here? That's possible. Ethan is here.
Type 1 is failing to
Reject the null.
reject the null, and type 2 is you fail to reject it.
So we're going to emphasize that was a mistake when you did it. So we want to say, there's a long way to say it, but I'm just going to say, mistakenly. Rejecting the null. Mistakenly failing to reject the null.
What's an example of these things? What's an example of these things?
Oh,
Mm-hmm.
so they don't want you bought you bought a car.
Mistaken. I don't know why I added the ing here. Mistaken. Okay, you bought a car.
When you bought the car
Okay, so maybe because the car is
is
Mr. Bunny, like maybe it's busted, or maybe it's an ugly car and you weren't thinking, or maybe it's on fire and you didn't look at the car beforehand. Like, why not buy a car that's on fire? What are you doing, Hank? So, but regardless, you're absolutely right. So it's you're buying a car you shouldn't have. Is that a type 1 or type 2 error?
that's type 1
Type 1, yeah, absolutely. Why?
because the law is to not buy a car.
Mm-hmm.
You
Exactly. You did the unusual thing, and that was a mistake. Right, exactly.
Alright, excellent. Can you think of a type 2 error? You want to think of a type 2 error? Yeah, CJ.
Someone, you hire somebody with mismatches.
Well, that's a type 1 though, right? The usual thing is to not hire people. I mean, your null hypothesis is to not hire people. So if you decide to hire someone you should have, that's like buying a car that you should have. Anyone else? Michael?
hiring a person, but that person has a problem with hiring a worker.
That's exactly what CJ said. You hire someone to do that. So, I can remember your name.
You don't have
Charlie.
Maybe like not hiring someone that would have been
So going the opposite way, right? So yeah, you're speaking with your null, or you're failing to reject the null, but that was a mistake. So, one of the interesting things about this,
That type 1 errors are in general more self-correcting than type 2 errors. Why do you think I say that?
is that what you're saying?
because you don't know you're going to touch it there.
Yeah, exactly. Tell me more.
And you just never know what you're missing out on.
Mm-hmm.
Like, if you don't hire that person, you would never know that they can make a lot of money for your company. So,
Yeah.
you just never know.
Exactly. There might be some rare exceptions to that, like maybe that person goes on to be famous, or you're hiring actors and you reject someone, or you're like all the people that like rejected Harry Potter, right? And then Harry Potter goes on to be like famous, like, oops, right? That was a type 2 error. Made that mistake. All the publishers and everything. But in general, yeah, I was absolutely right. You typically don't know that you made a mistake when you make type 2 error. But when you make type 1 error, precisely because you do the unusual thing, that you discovered that, it's going to stand out that was a mistake. So a classic example of this, or an important example of this, is the FDA, the Federal Food and Drug Administration. They approve drugs in the United States. In order to get a drug approved by the FDA, you have to demonstrate in the analysis that it is A, safe, so it doesn't make people worse off, or at least doesn't make people worse off in some significant way, right? Everything has side effects. And B, it's effective. So it does what it sets out to do. It improves people's health, whatever they're trying to improve. Now, this kind of analysis requires statistical analysis. It's a medical, you can't test literally everyone. You can only test a sample, so there's always some chance you'll miss something. If they approve a drug that is not effective, or maybe even dangerous, that's type 1 error. Right? What's their default position? If the drug comes up, what's their default position? Not approve it, right? So if they did the unusual thing and said, we're going to set this out into the world, that's type 1 error, right? When they shouldn't have, right? They set it out into the world, it has some problems, maybe it increases the risk of heart attack, type 1 error. And it's really clear that it happens. By definition, everyone knows about it. And so there's a sort of self-correcting here because everyone knows about it. Then the drug can be pulled. Yes, it's unfortunate. Some people suffer, maybe even die, but it is at least limits the damage. What would be the type 2 error that the FDA can make? What would be the type 2 version? Rejecting a beneficial drug, or maybe failing to reject the null.
Yeah, exactly. Tell me more. Jeanette is what I was going to say. So, Jeanette, tell me more. What do you mean?
I mean, again, this is something you never know.
Yeah, exactly right. It never gets out there. And in some ways, this is even more dangerous because we never know. There's this great thing which could save lives that could be out there, but is not, and we never hear about it. So there's, but from the FDA's perspective, from their incentive structure, this results in bad press. Type 1 error results in bad press. Type 2 error results in no bad press because we don't know about it. So even though this one is more dangerous, its real danger relies on our lack of understanding, and as a result, it's more common. And there's some evidence that suggests that the FDA is overly cautious because they're really concerned about type 1 error, and thus they end up making a lot of type 2 errors. Here's an example of the sensor pad, which is a piece of, it's 2 pieces of plastic sandwiched together with a little bit of oil between it. And the whole idea is it increases your sensitivity to touch, which is incredibly useful if you're, say, checking yourself for breast cancer, or really any kind of cancers, but often breast cancer. Well, obviously this is safe, right? It's not going to harm you if you use it. It's not a pill that you put in your body. And it's also effective. Anyone who handles it for a little bit immediately can tell, oh, this is effective, this works. Increases my sensitivity. But the FDA, when it was sent to them by the company, didn't know how to handle it. It was like, it's an unusual device, right? There's no technical issues behind it. It's not a piece of medicine. It's not some drug. So they categorized it in the high risk category, which required it to be extensively tested. With random trials, lots of people using it, testing their blood pressure, testing to see if their life gets shorter as a result of using it, testing to see if they develop any sort of other diseases as a result of using it. It's ridiculous, right? It was a ridiculous burden that this company had that was put on them in order to demonstrate that it is safe and effective, right? Obviously it is. They're making type 2 error. And the company got so irritated at the FDA, they just sent it out to hospitals anyway. So do you know what? This is stupid. We'll just give you the this is going to save some lives. And they just put it in the hands of hospitals. And the FDA amazingly rated hospitals to take these devices back because they weren't approved. Using unapproved medical devices. That's how they categorize it. But they were there long enough for people to get their hands on it, for actual patients to get their hands on it. And they started, it went to Congress, and patients testified before Congress saying, this device saved my life. I detected cancer because of this device. I couldn't detect it beforehand, but because I detected it early, and of course, detecting cancer, any kind of cancer, the earlier the better, that can save lives. And so, that problem was eventually solved and it was approved. But you can see how very easily we would have never noticed it at all. Had not the company broken the law and sent it out to people, we wouldn't have those people testifying before Congress. So one can only imagine how many other things are slipping through the cracks that aren't so obviously mistakes. Any questions on this? Okay. So, we also gave you some math. I gave you a little bit of math last class. It was the z-score. So I sometimes say z-score and I say z-value. I use them interchangeably. It's annoying. I apologize for that.
I'm trying to stick with just one.
I don't think, though, I removed all references to the other. I think you usually use. I believe. So I'm going to try to stick to one. But just keep in mind that in practice you will see them alternatively.
What was the calculation for this?
You can kind of already see on the board what I raised from last time.
The average,
The average of what?
minus standard deviation.
The average of what?
X.
X bar, right? The average of our sample. Minus mu.
Over, sigma.
Yes. Divided by sigma. Squared by.
And this is the z-score, right?
Yep, this is our calculated z-score. Now, when we get it, we will get some calculated value. And then we'll compare that calculated value to what?
Critical values. Based on significance levels. Well, significant levels. And really at a 90% one as well. I should really take that one out. I mean, it's there because I guess sometimes people tend to use it, but it's just sad that people say it's significant at 90% confidence. That's just sad. That's desperate.
Typically, 95 is the typical acceptable minimum. 95. And so, of course, based on that, based on if it's a one or a two-tailed test, and the level of statistical significance, you will get some critical score. And if this value is what? Larger, exactly. If it is larger than the critical score, then you claim statistical significance.
I want to put it here.
Calculated value is greater than or equal to critical. Now, we have not, if this is the case, if it's statistically significant, we do not prove that there is a difference. Why don't we say prove? If, for example, it's statistically significant, e.g. Yeah, let's say 90 at 99% confidence, which I believe the critical value is 2.576. All right, yeah. If it's greater than 2.576, let's say it's statistically significant at 99% confidence. Have we proven that there is some difference, or that there's some improvement, or the machine doesn't work? Have we proven that?
Aziz, what does 99% confidence, what does that 99% mean?
You're gonna pass? Yeah. Okay. Do anyone else want to try to answer it? What does that 99% mean, TJ?
So you're 99% confident except for data outside the population.
No, there's a 99% chance, right? There's a 99% chance that this difference is not due to some random error, right? That, as you point out, that sample mean does represent a new population distribution. Okay. Which means if there's a 99% chance that it's not a coincidence, there is a 1% chance it is. So we could claim statistical significance, but be wrong. We could reject our null hypothesis, but be incorrect. We could make type 1 error, in which case there's a 1% chance that would make type 1 error. What is 1 minus 99%? No. 1 minus 100% minus 99%. Is 1% or 0.01, which would be alpha. Alpha is the same thing as the chance of type 1 error. Alpha equals type 1 error. That is going to be the case whether we're talking about a 1 or a 2-tailed test. Alpha is type 1 error. You might wonder then, what is the chance of type 2 error? We call that beta. We're not going to get into that. That's a little more complicated to calculate beta. But if you're ever curious how it works, you can Google it. It's a reference to the power of the test. I think I have a couple of things on YouTube that I taught this in this course. I don't teach that part anymore because it's kind of complicated. It's not really something that's typically covered in introductory stats. So I took it out. Okay. Any questions so far? So far, this is basically what we talked about last time. So, let's go to something slightly new. Let's imagine that we do have statistical significance. Let's imagine that we were checking to see delivery times of our product. We were noting, oh, because we reorganized our system or because we're using some new program, the delivery times have fallen by 5 minutes. So they're 5 minutes faster than they used to be. And we run some numbers and we find it is indeed statistically significant, this 5-minute difference. Do we care? Is that a big deal? Are you shaking your head no?
No, I mean, you just care that they're right. You don't necessarily care what they're right about. That the 5 minutes is statistically significant.
Well, I mean, what do you mean that it's like let's imagine, for example, that these are deliveries that are from China to the United States. So typically they take a few days, right? If we go by boat, I think they take a few weeks. And I find that if we use a new system, it's 5 minutes faster if we use the new system. And we have an N large enough, we counted enough ships or enough deliveries large enough to know that it is indeed statistically significant. So, but it's 5 minutes.
You're asking, is it?
I'm asking, like, yeah, what should we do about that? Or do we care?
Don't think you care.
We don't really care. Yeah, 5 minutes. Who cares? The cost involved in switching over to some new system might actually be quite large. And yes, we can be confident that this is an improvement. It's only a 5-minute improvement. Who cares, right? So we do talk about statistical significance, but seeing as this is a BS 8210, this is business statistics, we should also talk a little bit about that business side, and that's what we call practically significant. If stat sig, if statistically significant, it may or may not be practically significant. It may or may not matter. Is the difference large enough when you consider other factors
You can't.
It costs to switch over. And other factors like cost, preferences, urgency, whatever. There are many different parameters you can consider, you might think about. But I'm just simply saying, look, just because you found statistically significant doesn't mean you've technically found anything from a business side that is interesting. I'm really confident that if we move our headquarters from Maryland to Virginia, we will save $80 a year. Whoop it frickin' do. Not worth the effort. I don't care if it's 99.999% confidence, not good enough for me to switch over. Keep in mind that in order for something to be practically significant, it must also be statistically significant. If it's not statistically significant, you don't know what's going on. In the realm of things that are statistically significant, some part of them are practically significant. But nothing. There's no overlap between the practical significant and the not statistically significant. Anything that is practically significant is by definition statistically significant. Any questions on that? Anything that is practically significant must also be statistically significant. Because if it's not statistically significant, then you don't really know what's going on. It's like, well, it looks like there was no difference. And if there's no difference, it can't possibly be interesting. It can't possibly be worth it. It can't possibly be, from a business perspective, worth your time. Like, I don't think the complaints will change at all. Like, well, then we're not going to do it, right? I don't think this will increase our ratings at all. Okay. I can't tell. I can't tell if this matters. All right, well, then I guess it doesn't. Any questions? No? Okay. So far, we've done this one, the Z statistic, which says, oh, we know the sigma, we know the population standard deviation. It's nice to have that information. Sometimes you have that information, and sometimes you don't. In fact, often you don't. Depends on what sort of data you have previously. If you don't have sigma, how do you get an idea of the dispersion? So you have a sample. You're able to figure out X bar because you can take the average. But how do you get an idea on what the dispersion of the population is if you don't have sigma? You don't have the population dispersion, population standard deviation. How do you get an idea of the standard deviation? No, I mean you do, but what's the formula?
This is standard deviation. deviation. Exactly. Thank you. So, if you don't know the population standard deviation, you have to rely on the information you have to estimate it. You rely on the sample standard deviation. So the only difference between this equation, where you know sigma, and this equation, is that we use S instead of sigma, the sample standard deviation. Other than that, it's the same, though it equals something different. What does it equal?
TX bar. This is the ZX bar, this is TX bar.
We can't rely on our standard normal distribution if we don't know sigma. We have to rely on some distorted version of it, someone that has fatter tails than normal. It's really a family of distributions, anti-distribution. Dependent on our critical value will depend not just on our significance level, 95% or 99.9%. What else does our significance level depend on? Our critical values, I should say. Our critical values depend on. I'll give you a hint. It's the same thing that matters when we did this for confidence levels, for confidence intervals, I mean. Anyone? Give me another minute.
You have to put in the degree.
Hmm?
You have to put in the degree.
Ah, okay, that's right. This is right.
Yeah.
Yeah, it's okay. All right. We need to figure out the degrees of freedom, which of course equals n minus 1.
This matters because the more observations we have, the more reasonable our standard deviation is, or estimation of the standard deviation. So as n increases, degrees of freedom increase. As degrees of freedom increase, our critical t values that we'll be comparing it to will get lower, will become more reasonable, will approach our z values. And I'll show you how to find those in Excel.
I have a question.
Yeah.
For the degrees of freedom, are we talking about degrees of freedom, or I just want to know what it is?
Well, you need to know what it is, but I mean, it's a simple enough equation because it's n minus 1.
So what do you use?
You use it to find the critical values for t sets. All right. Last one.
Z. I'm gonna erase this part.
For z sub p, or I should probably call z sub p bar. Sometimes I use p, sometimes I use p bar. I need to fix that. So bear with me for now. This would be the calculated value for a proportion. So here, x bar can be anything. It can be 0, it can be -8, it could be 563. Right? Maybe we're counting, how much something costs, or maybe we're counting how long it takes to do something. C, just like when we did confidence intervals, stands for what? Charlie, remember what P stands for?
Proportion.
Proportions, right? Later it'll be probability, we're writing out proportions. So exactly, what does proportion mean? Yeah. What does it mean just in general?
It's percentage of
Mm-hmm. Yeah, exactly. It'll be bounded between 0 and 1 because we're always going to express it as a decimal. Right? Interestingly, same sort of with probability as well. Always expressed as a decimal bounded between 0 and 1. So we will say P, or P bar, I should say, just to make it symmetric, minus, and now we're going to need to compare it to some pre-existing standard, which will be pi, the Greek letter P. And then we take the square root of pi times 1 minus pi all over n. And just like before, we will take that z-score that we will calculate, we'll compare it to some critical value, and we'll check to see if it's statistical or not. The end. Any questions about these three things? No? All right. Let's fire up Excel. So if you want to go ahead and right click and maybe create a new, what's it called? A new Excel spreadsheet, thank you. So this is the one I have. It's simple, yeah. Go ahead, Dave.
why is pi 22?
Because I set up some sort of, equation in that. If you look at it, imagine your point expansion 26 and then there's related how to go to it. We'll go through that example. Okay. So, Excel does not have these equations built into it. So what we're going to do is we're going to set up the inputs. It's sort of like here's x bar, here's mu, here's sigma, etc., etc. And then we'll calculate it ourselves, and I'll show you the stages for calculating. I'm just going to do it that way because then you can see the parts and we can change things if you want. So let's see, what do we need? We need a mu, we'll need an x bar, we'll need a sigma, and we'll need an n. It's about, that's about as I need 3 lines below. Oh, and I need 2 lines below. All right, numerator, denominator, and calculate value. So, let's imagine we want to know if our new sports drink improves athletic performance over what people would normally do. So we did a bunch of, we know that, for example, we decided to grind because that's a simple thing to test. So we know that the average athlete, people that are really interested in science, takes 15 minutes to run a mile. We give the sports drink to exactly, I think it was 16 athletes and have them run a mile again upon drinking a sports drink, and they run a mile in 13.75 minutes. We have a standard deviation, a sigma, I should say, exactly 2 minutes. Population standard deviation. And we have consistency. Did it improve anything? So our first question is this a one or a two-tailed test? Did our sports drinking improve athletic performance? One-tailed test, how do you know? What? Mm-hmm. Exactly.
Well, then aren't we done? Because this is lower. And so obviously it wasn't an improvement.
It was? What do you mean?
It's an improvement on time that it took them to read them out, so.
It's lower.
But in this case, a lower number is an improvement over our.
Exactly. So, at least this bit of temptation, we always want to think, oh, bigger numbers are better. And sometimes they are. You know, if you're talking about how many sales you got, or you're talking about how much interest, or how much customer traffic, or what, or you know, how much revenue you got. But there are some things which larger numbers are worse. What are some things worse? Like, so speed, obviously, and this is something I see people make a mistake on all the time on exams. They think, like I say, which person did it faster, and they will then like focus on the people who took longer to do things, because that's a larger number. Like, no, they did it slower. Right? These people, this one was faster, right? But something else too, where smaller number suggests an improvement. What would be another example besides things related to time? Oh, sure, right? So get a lower score, right? Fewer swings. Anything else?
Yeah. I was just thinking, like, there's things at the gym where, like, there's like assisted weight. Like, if you can't pull yourself up, you can assisted weight, and like the lower the weight, kind of stronger. Like the less assistance.
Oh, I see. So less assistance. Yeah. So rather than you, because that equivalently amounts to more weight that you can do, right? But it's less assistance. Excellent. Other examples are things like there are fewer complaints per person, or fewer mistakes for an employee. Okay? Any number of things, fewer costs, lower costs, whatever you're doing.
Any number of things can be improvement if they're lower numbers.
You give me a bunch of sports examples.
It's not those things. So for the new, so we're gonna have to calculate it. Let's calculate the numerator first. We'll look at the numerator here. Exactly. But we won't type in 13.75. I'm just going to set up B2. Because that way we can change it later if we want. Minus B1. I'm asking this to switch to this so you can see the equation as I put them up. What's in our denominator? One, two, 4. Exactly. So you can type in 4, or you can type in square root SQRT B4. Finally, we need to find the calculated value. So what would be our calculated value? How would we put that? What was that, Jack? P5 over B6. I want to do one thing before that. I want to take the absolute value. ABS gives us our absolute value, and then we can do B5 divided by B6. Does everyone have this? Yeah. So, what do we get for our result? 2.5. Alright. Is that statistically significant? Anyone? 95 it is. Yep. How do you know?
Because it's less than 9 averages here. It's less than 4.56. And it's more than 1.96.
Yeah, absolutely. What'd you say, 2.56? I agree that it's specifically at 95. Was this a one or two tail test? One tail test. So is this specifically at 99? Yes, it is. So that's crucial with you. Maybe they might call that. Or if you don't remember, I don't know, maybe just, let me just show you how to find these values, by the way, in Excel. We're going to call these alphas. And it'll be, what's the alpha in 95% confidence? 99. And I'm going to call this our one tail. And we'll call this our two tail. So, let me show you the equation for it, and I'll unpack it for you. It's easier just to show it to you. And then you work with it. Yeah, I'm going to go over this thing. And show you the equation. I'm also going to shrink this out. So, note that when I did that, I got 1.645, which is our standard for one tail test and 95% confidence.
I got that by first using the standard normal command. So we are using a normal distribution with a standard deviation of 1 and a mean of 0. That is, and if you recall, if you pull that up, it asks for the z-score. If you use standard normal. Let's do this. Zero. Let's take my 1. I'm asking for inverse because I want the area on the curve. I want to know this area. Well, that's that right there. 5% would be this area here, and by definition, the critical value is the distance from 0. This is the distance from 0. How far away from 0 can we get 5% on one tail? I take the absolute value because I'm going to the left. So I need to make it positive. And when you do that, you get 1.645. You can copy and paste it, and you can recognize the other ones too. By the way, I think there's a mistake in my notes because my notes say it should be 2.330, but obviously it's 2.326. So I think that I miscopied something down when I was writing my notes. I think I put in 2.33. Whenever I was looking at it, I was set 2.33 because it was rounded to 2. That was rounding to 3, and I forgot to double check to make sure that was correct at three places. Obviously, it should be 2.326. My notes are wrong. This is right. But you can see we're just recalculating the whole thing. And what's fun too is we can put in anything for alpha, right? We can put in 0.03. We can find 97% confidence. That's the problem. So is it statistically significant? Yes, because 2.5 is greater than 2.326. Any questions? I know what you're thinking. How would I do this to the two-tail? How did I do that? This is one tail. Control time. So, how do we indicate one tail? How did we indicate one tail on our table? Z alpha, right? Z sub alpha. How do we indicate, this is one tail. How do we indicate two tails? Z alpha divided by 2. Well, this is our alpha. If we want to claim this is a two-tail critical values, we would take that alpha and split it in half. Which means this area has half the number of observations than before. Right? It's not 5%, it's 2.5%. So the easiest way to do this is to go in there, instead of D2, write D2 divided by 2. Out of it alpha, make it alpha divided by 2. And those are 1.96. Just like before. And copy paste, and now the other friends. 2.576, 3.29. Of course. So, I will give you those critical values on the exam, but for reasons that will become clear, I want us used to thinking about also all this stuff is there in Excel. You can just find it yourself too. And this, arguably, because you'll have the table, it's kind of redundant, it's going to be really useful when I show you the t-scores in a second. Any questions on this before we move on? No? Great. Okay.
Did you want to show the formula on the test? Is that what you just said?
Yeah. You can just look at the process exam, you'll see it, so you'll let you do it. At the end of the exam, the formula sheet, the information, that's a kind of exam. You will get the Z-scores, because that's an easy thing going through. In fact, I got all these Z critical scores. Critical values. Scores are values. Scores are values. That's it. However, let's imagine that for this example, and before we move on to, we got a calculated value of 2.5. That's statistically significant, obviously. Is that practically significant? Is that
1 minute and 15 seconds off our time notable?
In general, so we have a business, we make a sports drink, it shaves off 1 minute into 1 minute and 15 seconds off people's time to run a minute, to run a mile. Is that practically significant? It's statistically significant, but is it practically significant? You know, mile? Yes. For whom? What do you mean? What's an athlete? So we have to ask ourselves, this is the business part. Why do people want extra time? Are they running a race? In which case, I totally agree with you. Shaving over a minute off your time to run a mile is huge. And that's exactly who we should market to. But if we're talking about people who are just running for exercise, and they're like, oh, it takes me so long to do my exercise. I wish that I could just get the same result in less time. It's like saving them 1 minute and 15 seconds off their daily mile run is not going to make a difference. You know, we need to come up with a whole new exercise for them. Okay, because you can't you gotta get that. So unless you get something, I don't know what the hell we're giving them. That will cut the time in half. Something that would be important to them. So again, it's about who we're talking to. We're talking to racers. Yeah, I agree. This is huge. This is a big deal. This is how we should focus on marketing. If we're talking about casual people who are just exercising, I don't think they'll care about a minute. I think that's they're just trying to save something. Maybe if it's like some sort of conscience they have to practice, okay, that's a race. Okay, well let's imagine we don't have sigma. Let's imagine we have S. So we have less information. But for simplicity purposes, and we can even change it if we want. We can make that 2.3 or something. We can change but for illustrative purposes, I want to keep it the same. Because I want to show you how things change when the only thing we do is switch from a z to the t.
Well, obviously then, if the only thing we're changing is we're making that s, that 2 is still put in the same part of our equation. So the calculated value doesn't change. What does change are critical values.
We obviously have to use the t-scores rather than the z-scores. I'm going to copy paste the whole thing down. Oops. Copy. But we can't use this. We got to use something else.
We are, again, going to need to find these critical values. And this is where Excel really shines, because normally, if you wanted to find the critical t-values, you have to pull up this table, and then you have to look at the significance level I want to look at, and then cross-reference it with the degrees of freedom that we have over here, and then and only then do I find my critical value that I can compare it to. And that is not something I can put on an exam for you and give to you, because it's a whole big table. It would take up too much room. So I just tell you to use the command I'm going to show you.
That is the t-invert command, t-I-N-V. You'll see there's also an option for t-I-N-V 2t. That's the two-tail version. I'll show you that in a moment. But let's start with this one. Now, note it's not asking you for one piece of information. Right? We obviously will need that, so we'll put that in. The alpha, the probability.
It's also asking you for this. What is that? Can you read it?
Excellent, Einstein. I'm sure you read it on this and that over there. Yeah, degrees of freedom. Yes. I'm sorry, what was that?
Can't hear you.
Why did you use absolute value?
Oh, because I forgot to. Sorry. Yeah, I should put absolute value in. Thank you.
Let's look at that too. Because your instinct is actually mine is
I'm going to be doing the same thing over here.
Okay. So, what are my degrees of freedom here?
And that's n minus 2.
N minus 1 or 15 or B4 minus 1. Now, technically, we should also hit F4 there to lock that cell reference. To make that massive cell reference. Because when we copy and paste it down, we don't want it to like change, you know. Therefore, we're referencing something else. And there it is. 1.753. Of course, we copy it out for the formulas. There it is. And then we can take this exact thing, copy and paste it over here, and then change that t.inv to t.inv.2t to get the two-tail version. But don't copy and paste the cell, copy and paste the contents, otherwise your D9 will change. Oops. Damn it. Oh, or you can go. And we will just make that press 2t. It says B4, I'm sorry, it says B5 rather than it was B4 before because we added a row at the top, if you recall. Now we have our T critical values. So, It was 2.5 before. Is it statistically significant? And 99% confidence? Is it statistically significant and 99% confidence? No, it is no longer. Why? Calculated value is less than our critical value. So again, this emphasizes that importance, right? The only thing I changed is I said, you know what, that 2EI, it didn't come from sigma, it came from our own estimation of sigma, and that resulted in us having a higher critical value, and that resulted in us saying, well, we don't really know even at 99% confidence. We still know it at 95. But we don't know it at 99. Any questions? Last one. A couple of minutes we have left. Let's do proportion. So, I'm going to switch gears slightly. Let's imagine we work in a growing trucking business. We want to know how its recent expansion has affected the business operations. So, we're going to need I and R then. Let's imagine before the expansion, 20% of deliveries were late to their destination. And after the expansion, 28% out of 100 deliveries, so we checked 100 deliveries, 28% were late to their destination. So for pi, we're going to put in 0.2. For pi bar, 0.28. And what is n? 100. And then just like before, we're going to set up a numerator and a denominator. Of course, and then I calculated that. And I'm just going to type it up. Like that. Like that. The denominator is going to have these square roots. Pi times 1 minus pi divided by n. So that's our denominator right there. Right, pi 1 minus pi n. Yep. And then you just take the absolute value. That. That's nice and clean. Of course. I did that really quickly. I'm running out of time, sorry. I wanted to. Again, you can follow this really carefully. I break down the numerator and the denominator because I think it's a little easier to follow all the steps, so you don't have like layers of parentheses to get the order of operations right. You know, it's useful to do it that way, especially when you're first learning or when you want to make sure you do it right. When you're doing a bunch of these, you kind of want to condense it all into one thing, so you can have the whole equation in one cell and then copy and paste it. But here, I'll just split it up. I don't care. But here's our square roots. B 1 minus b all over n. Our absolute value of the numerator and denominator. The numerator is, of course, the difference between the two. Take that absolute value and get rid of any negatives. And we got a result of 2. Is this statistically significant? Is it statistically significant? Your first question is this a Z or is it a T? Z, right? So it says here we got a Z. So is this statistically significant? Yes, and 95. You of course just set that to. You recognize it as a two-tailed test. Because we're wondering how it was affected by the expansion. It could have gone up, it could have gone down. We don't know, did the economies of scale make it better, or is this just too hard for us to manage? Looks like it's too hard for us to manage. Right? We need to either scale down and fix the problem, or we need to reorganize and fix the problem.
But I would also argue that an 8 percentage point increase in our late deliveries, that's probably practically significant, right? That's pretty notable. To go from 20 to 28%, an 8% increase, an 8 percentage point increase, that's pretty notable.
All right, so next class, we're going to do more practice with this. I just have set aside that you're going to be practicing in groups, so it'll be a fun day. And I will see you on Thursday. Have a great couple of days, everyone.